Okay, welcome back. This is the last problem that I'm going to do for you. That is part of your problem 15. Chapter 4 is very focused. Give you a polynomial, find some roots. In this case, though, rather than go through the steps that we have developed here to find real and complex roots, we're gonna do something else. We're gonna find this root. We're gonna estimate this root numerically, with the caveat that we're gonna estimate it just as closely as you would like. And the procedure that we're gonna use, among many procedures, is called halving the interval. So this problem 92 on page 34 is a sister to problem 89 in your homework 15. So let me motivate it, and then as we get further down, I've sort of written down the answers here so you don't have to watch me make the sausage. You don't need to have a video with me operating my calculator. Let's imagine that we're asked to find a root here. We could sort of say there's at least 3 real roots. We could take Descartes' rule and find out where they might be. But at the end of the day, we've got to go find, make some estimates, find this root. And the rational candidates that we would look for have a numerator then, looking at 20, of 1, 2, 4, 5, 10, and 20, and a denominator of 1 and 1/3. So I'm not going to write those down. I'm just going to use them to think a little bit through this thing. Let's look at f of 1, for instance. 1 is a potential candidate for a rational root, but I get 1 minus 2, I get 1, I get minus 20, I get minus 21. So we missed it there. 1 doesn't work for us. I'm going to try 2, not 3. I'm going to try 2 in this case. And 2 is going to be 2 cubed is 8 times 3 is 24, minus 20 is 4, minus 8 is minus 4. So we're a little closer, but we're still 0. So the next candidate here, 1, 2, is 4. And let's see if we can figure out what 4 is. 4 cubed is 64 times 3 is what, 192, minus 20 is 172. Minus, this is 32, what I say, 170, so I think it's minus 140. It's plus 140. Right, this is because of this term. Took us up to 192, down to 172, down to 140. So something's happened here. The function at x equals 2 had a value of minus 4. At x equals 4 has a value of plus 40. I'm going to do a quick sketch. It's not very much information, but it's actually a lot of information in some ways. Because here's 1, 2, 3, and 4. And what we've shown is at 4, the function is way up here at 4, 140. But at 2, it's way down here at 2 minus 4. So what you do at this point is you appeal to what's known as the intermediate value theorem, which says that if you have a continuous function defined on an interval a and b, in this case 2 and 4, then the function will take on all values between f of a and f of b. It means if you have a continuous function, you want to plot it, and you have 2 points, you got to draw a line without picking up your pen between those 2 points, and therefore every value of f of x between f of a and f of b shows up. And in this particular case, since f of a, or f of 2, is negative, and f of b, or f of 4, is positive, that means that someplace the function, I don't know where, but it cracked through the x-axis. It has a root somewhere between 2 and 4. So you make use of that fact to just do this. We've calculated f of 2 of minus 4. We've calculated 4 as 140. We know somewhere between 2 and 4 there is a root. Let's split the 2 and 4 difference in half And let's see what happens at 3. Let's calculate f of 3. And when I do that, when I just insert 3 in up here, I get 43. Okay, well, let's think about that again. Now at 2, the function is negative. At 3, it's positive. Well, in the same way, here is f of 3 right here. Not very well to scale. But in the same way, there must be a root between 2 and 3. Great, let's get closer to it. Let's divide the interval from 2 to 3 in half, 2.5, and let's see if the root is between 2 and 2.5 or between 2.5 and 3. How do we do that? We put in x is equal to 2.5. We find that the answer comes out positive, and so there must be a root between 2 and 2.5 because the function's negative on one side, positive on another. Great, let's have that interval between 2 and 2.5, 2.25. I'll run it through the wash again. I'll find out that f of 2.25 is 4, also positive. So somewhere, in fact, sort of midway between 2 and 2.25, because 2 is minus 4, 2.25 is plus 4 and change. Maybe I'm getting pretty close to the root. I'll try. Halfway between 2 and 2.25 is 2.125. It's negative. That's just what I'll stop right there because you can see how this halving the interval works. Every time you take a step, you find an interval which must contain a root, and your next step is to halve that interval and make that next interval half your next estimate. So after just 1, 2, 3, 4, 5, 6 steps, we've got an estimate of the root of 2.125, and the actual answer here, I'm going to do this actual, two decimal points is 2.13, which is what you'd get here actually if you rounded that up. So you just did 1, 2, 3, 4, I don't even know if you did 5 iterations there to start to get some pretty good accuracy on that estimate. So that's the way halving the interval works. It is fairly slow to converge relative to some of its cousins, other numerical techniques, but it has a real advantage over some of its cousins, and that is it always works. It always converges to a root. Not true of some of its sexier, faster cousins who may or may not converge, or who may converge to another root that you didn't even know you're looking for. So halving the interval, pretty straightforward way to find roots numerically.